Electric vehicle charging technologies are the backbone of the global shift towards sustainable mobility. While the cars themselves often capture the spotlight, it is the ability to recharge quickly, safely, and affordably that determines whether electric vehicles can truly replace gasoline-powered engines on a mass scale. Charging systems vary in speed, infrastructure, and convenience, each with its own strengths and limitations. Together, they form a diverse ecosystem that is shaping the future of transportation across every region of the world. The most basic form of charging is known as Level 1. In North America, this means plugging into a standard 120-volt household outlet, while in most other regions, it's 220 to 240 volts. Level 1 charging is slow, often adding only a few miles of range per hour, but it is extremely accessible. No special equipment is required, making it ideal for overnight charging at home. For early adopters or drivers with short daily commutes, it offers a low-cost entry point. Yet, as adoption grows, its limitations become clear. Level 1 is simply too slow for mainstream needs. Level 2 charging represents the next step, and it has become the most common type for homes, workplaces, and public stations. Using 240 volts in North America and 220 to 240 volts elsewhere, Level 2 requires a dedicated charging unit. Delivering between 7.4 and 22 kilowatt hours, it can add approximately 60 miles of range per hour depending on the vehicle. With the average car able to travel some 4 miles per kilowatt hour, Level 2 strikes a balance between speed and affordability. Installation costs are higher than Level 1, but its practicality has made it the backbone of EV infrastructure worldwide. Companies like ChargePoint, Enel X, and Clipper Creek lead the market in this segment. For long-distance travel and commercial fleets, DC fast charging, often called Level 3, is essential. Unlike Level 1 and Level 2, which provide alternating current that must be converted by the vehicle, DC fast charging delivers direct current at 400 to 900 volts, bypassing the onboard charger. This allows rapid charging of up to 350 kilowatt hours, enabling 300 miles of range in just 20 to 30 minutes. It is critical for highway corridors, urban hubs, and fleet depots, but it comes with challenges: high installation costs, battery stress from frequent use, and the need for grid upgrades to support such power demands. Standards vary, with CHA Demo, CCS, and Tesla's supercharger network competing globally, though CCS is emerging as the dominant format in Europe with CCS2 and North America with CCS1. ABB, Tesla, and Siemens are among the leading manufacturers. Wireless charging, also known as inductive charging, is an emerging technology that could redefine convenience. Instead of plugging in, drivers simply park over a pad embedded in the ground, which transfers energy via magnetic fields to a receiver on the vehicle. Wireless charging offers automation and ease of use, particularly for fleets, taxis, and buses. But it is less efficient than wired charging, leading to energy losses, and remains expensive and limited to pilot projects. While not yet widespread, it could play a role in applications where convenience outweighs cost. Another innovation is vehicle-to-grid, or V2G charging. This technology enables bidirectional energy flow, allowing vehicles not only to draw power from the grid, but also to supply it back. EVs can act as mobile storage units, supporting renewable integration, stabilizing grids, and even providing backup power during outages. For consumers, VUG could create new revenue streams by selling energy back to utilities. Yet, the technology is complex, requiring advanced hardware, regulatory frameworks, and grid integration. Pilots are underway in Europe, Japan, and parts of North America, and the potential impact is significant. Each technology has clear trade-offs. Level 1 is cheap and accessible, but too slow. Level 2 is practical and widely available, but requires installation costs. DC fast charging enables rapid travel but is expensive and can stress batteries. Wireless charging offers convenience but suffers from efficiency losses. V2G provides grid support and new opportunities but demands complex integration. Together, they highlight the importance of a diversified charging ecosystem. Scaling EV charging faces challenges. Infrastructure gaps remain, particularly in regions with limited public networks. Grid capacity is another concern, as high-power charging constrain local electricity systems. Standardization is critical, since competing connector types create confusion and limit interoperability. Costs remain high, especially for DC fast charging installations, and consumer awareness is still limited. Addressing these issues will be essential to sustain growth. Yet opportunities are abundant. Ultra-fast charging stations capable of delivering 350 kilowatts or more are emerging, promising recharge times under 10 minutes, rivaling the convenience of gasoline refueling. Smart charging systems integrated with apps and artificial intelligence can optimize charging times and costs, reducing strain on grids and improving user experience. Wireless charging could expand in fleet and urban applications, offering seamless convenience. V2G commercialization could transform EVs into distributed energy storage units, supporting renewable energy and creating new business models. Regional manufacturing of chargers could reduce costs and strengthen local economies. Regional adoption patterns reflect differences in infrastructure, policy, and consumer behavior. In North America, Level 2 and DC fast charging dominate, with Tesla's supercharger network playing a major role and CCS1 gaining ground. Home charging is widespread due to suburban housing. In South America, Level 2 is most common, with Brazil and Chile leading adoption. Infrastructure is limited but expanding. Europe has strong regulatory support, with Level 2 and DC fast charging widely available. CCS2 is the standard, and V2G pilots are advanced in countries like the United Kingdom and the Netherlands. Asia leads globally, with China operating the largest EV charging network, including millions of public chargers. DC fast charging is particularly common in China, while Japan continues to use CHAdeMO and Korea invests heavily in smart city integration. Africa presents a different picture, with limited EV penetration and infrastructure challenges. Level 1 and Level 2 charging are most common, with South Africa leading adoption. Most charging is slow or home-based, reflecting the early stage of EV adoption on the continent. In conclusion, electric vehicle charging technologies are diverse and evolving. Level 2 and DC fast charging form the backbone of today's infrastructure, while wireless and V2G represent the frontier of innovation. Each technology serves different needs, and adoption varies across regions based on infrastructure, policy, and consumer demand. The challenges of cost, grid capacity, and standardization are significant, but the opportunities in ultra-fast charging, smart systems, wireless convenience, and grid integration are equally compelling. As EV adoption accelerates, charging technologies will remain the critical factor shaping the future of mobility, energy, and sustainability worldwide.
Fleet Mobility Today.